Welcome to Sleepy School, the place where you can let go of the day, close your eyes and drift into sleep while learning something new. Every night, you'll fall asleep a little wiser as history, science and stories become the background of your dreams. If you'd like, share in the comments where you're listening from. I genuinely enjoy seeing where everyone is. And don't forget to subscribe for a new sleep lesson every night, so your mind can keep growing even as you rest. Settle in, loosen your shoulders, let your breath slow down. We are going to take a calm walk to the far edge of what we can ever see, and then we'll look past that edge with our minds. The question sounds simple. How big is the observable universe? The answer is a careful one. It is not a fence around reality. It is a horizon, the farthest distance from which light has had time to reach us since cosmic dawn. Beyond that horizon, the universe almost certainly continues, perhaps without end. But observable means only what can have communicated with us so far. Before numbers, a few tools. A light year is the distance light travels in 1 year. It is about 6 trillion miles. A parsec is a little more than 3 light years. Astronomers like it for calculations, but light years are friendlier to the ear, so we will mostly stick with those. 1 astronomical unit is the distance from Earth to the Sun. Distances in space come in flavors because space itself expands. And that expansion subtly changes what we mean by how far. Here is the headline, wrapped in gentle qualifiers so we do not pretend to more certainty than we have. The observable universe has a radius of about 46.5 billion light years. That makes the diameter roughly 93 billion light years. This seems odd the first time you hear it. If the universe is around 13.8 billion years old, and nothing outruns light, how can anything be more than 13.8 billion light years away in any meaningful sense? Because the space between points is not a rigid stage, it stretches. Imagine dots drawn on the surface of a balloon. Do not imagine the balloon in the air, imagine living on the 2-dimensional surface itself. As the balloon inflates, the dots do not sprint across the surface, but the surface between them grows. When the light we see today began its journey from the far horizon, the place it left was much closer to us. While that light was in flight, the space it traveled through expanded. If you freeze the universe now by cosmic time and ask, how far away right now is the place that sent the light we are receiving now? You get that larger number. The co-moving distance of about 46.5 billion light years. Because expansion complicates distance, cosmology uses several distance ideas. Look-back time is how long the light has been underway. Luminosity distance is the distance you would infer from how bright a standard candle appears, after accounting for redshift. Angular diameter distance tells you how big something appears on the sky given its true size. Co-moving distance is the separation you would measure between 2 points if you could pause cosmic expansion at the present moment. When people quote the size of the observable universe, they mean that co-moving radius. To feel the scale, let's climb a ladder, rung by rung. Start close to home. The Earth-Moon distance is about 1.25 light seconds. A radio call to the moon and back takes about 2.5 seconds. The sun is about 8 light minutes away. Even sunlight is not live. You always see the sun as it was 8 minutes ago. The far edge of the planetary family sits in a sphere called the Oort cloud, a reservoir of icy bodies a light year or more from the sun. Already the sun's gravity is whispering, not shouting. Step up to stars. The nearest star system, Alpha Centauri, is a little over 4 light years away. If you fired a beam of light at it tonight, it would arrive in the middle of the decade to come. The Milky Way, our galaxy, is a broad disk about 100,000 light-years across, with a central bulge and starry spiral arms. Our sun orbits the center once every couple 100 million years, dragging along a family of planets like a tiny procession circling a city. Beyond the Milky Way is the local group, a small cluster of galaxies a few million light-years across. Andromeda is our majestic neighbor, on a slow-motion collision course with us. On even grander scales, galaxies connect in filaments, cosmic strands hundreds of millions of light-years long, threading around vast, nearly empty voids. These filaments lace into superclusters, and the superclusters arrange into a foam-like cosmic web. Zoom out far enough and you start to see a statistical evenness. On scales of a few 100 million light-years, the universe looks homogeneous, meaning no special places, and isotropic, meaning it looks the same in every direction, at least on average. We live in that smoothness, stitched together by gravity and history. Now return to the horizon. The light from the most distant thing we can see is not the light of a star or even the light of a galaxy. The deepest background is a cool wash, the afterglow of the early universe, the cosmic microwave background. It comes to us from a time when the universe was about 380,000 years old. Before that time, space was hot and dense, filled with a plasma of free electrons and protons that scattered light like fog scatters headlights. As the universe expanded and cooled, electrons and protons combined to form neutral hydrogen atoms. Space turned transparent. The photons present at that moment began traveling almost freely. Over billions of years, they were stretched by the expansion of space from searing visible light down to microwave wavelengths. Today, we measure that background as a nearly uniform glow, with a temperature of a little under 3 degrees above absolute zero. Think of the cosmic microwave background as a kind of photosphere, a last scattering surface. We are not looking at a wall. We are seeing back to a time when the fog cleared. Farther back in time, visible light cannot get to us because the medium was opaque to light. Other messengers, neutrinos and gravitational waves, could in principle show us earlier times because they pass through matter more easily. But for ordinary light, that glowing shell is the oldest picture available. So why is the horizon about 46.5 billion light-years away if the light has been traveling for about 13.8 billion years? Because the space it crossed kept expanding. The photons you catch tonight from the microwave background left when that matter was much closer to us, tens of millions of light-years away, not tens of billions. But by the time the photons arrived, the universe had swelled. If you mark where the light left and where it arrived, and then you ask for the present-day separation of those points, you get the larger number. That is the essence of the balloon surface analogy. Now let's talk about motion without motion. In everyday life, recession means an object is moving through space. In cosmology, galaxies beyond our local gravitational neighborhood recede from us because space itself is expanding. Their light is stretched on the way to us. We say it is redshifted because longer wavelengths are redder than shorter ones. The relationship between distance and recession speed for nearby galaxies is called Hubble's law. Recession speed is proportional to distance. Measure the slope of that line and you get a number that tells you the expansion rate today. Different methods give slightly different answers, which is a lively and unresolved debate. But the broad story does not change. The universe is expanding, and on the largest scales that expansion dominates over local gravity. There is a subtlety here that matters for our intuition. Because recession is baked into space itself, distant galaxies can appear to recede faster than light, without violating relativity. Nothing is outrunning a light beam locally. No galaxy is breaking the cosmic speed limit within its neighborhood. But over very large distances, the fabric between us and that galaxy is stretching fast enough that the total separation grows at a rate that exceeds 1 light year per year. That is allowed in general relativity. Physics is not broken. The expansion is not only happening, it is accelerating. Over the last few billion years, the expansion rate stopped slowing down and began to speed up. We give the cause a placeholder name, dark energy. It behaves not like matter or radiation, but like an energy density of empty space itself, something that does not thin out as the universe expands. A simple model is the cosmological constant, a uniform energy that fills space. Whether dark energy is exactly that or something more exotic remains an open question, but the acceleration shows up in multiple independent measurements. Distant supernova used as standard candles, patterns in the cosmic microwave background, and the characteristic scale imprinted in the clustering of galaxies called baryon acoustic oscillations. These are the ruler marks and yardsticks of cosmology. Once expansion accelerates, a second kind of horizon appears, distinct from the observable limit set by the age of the universe. The first one, the particle horizon, is how far light has gotten to us since the beginning. The second one, the event horizon, is the farthest distance from which light sent today will ever reach us in the far future. Because expansion is speeding up, there are galaxies we can see now, faint and redshifted and ancient, that are already beyond our event horizon. Their current and future light will never arrive. In fact, as the ages pass, light from more and more distant galaxies will be stretched until it is undetectable. The cosmic web will thin out of our view. In the unimaginably distant future, observers in our gravitationally bound neighborhood may find themselves in a lonely island of stars, with almost no evidence left in the sky that a grand web ever existed. This two-horizon story helps with the original question. The radius of the observable universe today is set by the age of the cosmos and the integrated history of expansion. That is the number near 46.5 billion light years. But the subset of the universe that we can influence going forward, places that could ever receive a message we send now, is smaller, because acceleration pulls the far distances out of causal contact. The particle horizon grows with time. We see more as light from slightly more distant regions arrives. The event horizon, by contrast, is a limit on our future light cone in an accelerating universe. Let's connect this back to what we actually measure. The cosmic microwave background is not perfectly smooth. It has tiny hot and cold spots. Those are slight over and under densities in the early universe that later grew into galaxies, clusters, and the cosmic web. The size of those spots on the sky, combined with how matter and radiation interacted in the first few 100,000 years, acts as a standard ruler. It lets us infer the geometry of space on large scales. The result is that space appears very close to flat, which in everyday words means Euclidean. Parallel lines stay parallel. Triangles have angles that add up to 180 degrees and so on. If the universe is curved at all, that curvature radius is far larger than the observable patch. Flat does not guarantee infinite. You can make flat spaces that are finite by clever topology. But the simplest reading is that if there is curvature, it is so gentle we do not detect it yet. Redshift is our time machine dial. The higher the redshift, the farther back in time we are looking. We catalogue galaxies by redshift, we date the light, and we reconstruct the growth of structure. Very distant galaxies appear small and dim because of distance, because of redshift, and because we are seeing them before they had time to form many stars. The galaxies we see at high redshift are toddlers by cosmic standards, clumpy and irregular compared to today's graceful spirals and giant ellipticals. Telescopes have been pushing this frontier outward, teasing out older and older starlight, but there is a hard limit for light. Beyond the recombination epoch, the universe was opaque. To reach earlier events with messengers, we need neutrinos or gravitational waves. Those backgrounds exist in principle, but they are extraordinarily hard to measure. How big, then, is everything beyond what we can see? The honest answer is that we do not know. The observable universe is a sphere centered on us only because we are asking from here. Someone far away would draw a different sphere centered on them. The whole, whatever that turns out to mean, could be spatially infinite. It could be finite but unbounded, like the surface of a sphere but in 3 dimensions, where you can travel forever without hitting an edge and still never run out of space. It could be flat and infinite, or flat with a multiply connected topology that wraps around in strange ways. What we do know is that on scales we can observe, space is extremely flat and uniform in its average properties. That alone suggests the total is vastly larger than our patch. Inflation, a leading idea about the earliest fraction of a second, amplifies this sense of vastness. According to inflation, the universe underwent a burst of extremely rapid expansion very early on, smoothing out curvature and ironing away relics of any previous state. If inflation lasted even a bit longer than the minimum needed to solve puzzles like the horizon problem and the flatness problem, the result would be a region of space much, much larger than our observable bubble. Some models of inflation even imply a bigger structure called a multiverse, with many bubble-like regions with different initial conditions. That is speculative. It is a working theory, not a closed case. But it captures the logic. If the mechanism that made our observable universe smooth and flat operated for longer than the bare minimum, then the full stage is immense beyond imagining. Let's walk back from the theoretical horizon to the craft of measurement. How do we get those distances and ages with confidence? Multiple independent ladders intersect. One ladder starts close to home. Parallax, the slight shift in a star's position against background stars as the Earth orbits the Sun. That gives direct distances to nearby stars. Then come standard candles, objects of known brightness, like certain types of variable stars and type 1 as supernovae. If you know how bright something truly is, you can infer its distance from how dim it appears. Another yardstick is the imprint of sound waves in the early universe. The Baryon acoustic oscillation scale, visible today in how galaxies cluster. The cosmic microwave background provides the earliest snapshot and the largest ruler. Fit all these together in a consistent model, and you triangulate the numbers. You do not rely on a single shaky board. A word about counts. How many galaxies live in the observable universe? The honest range is hundreds of billions, with uncertainty at the high end. Earlier estimates suggested perhaps a couple trillion. Newer deep surveys imply fewer small galaxies than we once thought, which leans toward lower totals. The details are still being revised as telescopes image the faintest smudges. The exact count does not change the main picture. On any human scale, even the low end is a vast population. The observable universe is crowded enough to humble us, empty enough between islands to stretch our imagination. Now let's translate the big numbers into something more tactile. If the Milky Way were a dinner plate about 25 centimeters across, the distance to Andromeda would be about 5 meters. The nearest big cluster of galaxies, the Virgo cluster, would be dozens of meters away. The observable universe would be a sphere kilometers across. These analogies are imperfect, but they remind us that emptiness dominates. The universe is mostly space, and space is mostly nothing. The matter that makes stars and planets is a small fraction of the total cosmic energy budget. Most is in forms we infer rather than directly see. Dark matter, which tugs by gravity but does not glow, and dark energy, which acts like a pressure that accelerates expansion. We map their fingerprints, but we do not yet fully understand their nature. 2 more clarifications keep our mental picture honest. First, center talk can mislead. The observable universe is centered on us only in the sense that a horizon is centered on each observer. Every galaxy sees itself at the center of its own observable sphere. There is no special place that is the center of the whole. The expansion is not a bang from a point into pre-existing emptiness. It is an everywhere event in which distances between free-falling points increase. Second, beyond the observable is not a mystical realm. It is just the region whose light has not had time to reach us yet. As time goes on, we see a little more of it. But because of accelerated expansion, there are parts we will never see, no matter how long we wait. Both things are true at once. Our particle horizon grows slowly. Our event horizon limits us forever. It is worth asking why the answer matters. The number 93 billion light-years across is almost cartoonish in its hugeness. But the habits of mind that produced it are down to earth. Careful measurement, multiple methods, relentless cross-checks, and an appetite for doubt. We did not sail to the edge in a ship. We traced the ripples left by ancient waves. We surveyed the sky for tiny temperature spots. We used exploding stars as yardsticks. We described the simplest model that fits all the data at once, and we keep prodding it to see if it breaks. So far, it holds. There is also a human comfort in placing ourselves. We are small, yes, but not lost. The laws that shape the whole are the same laws that operate in your teacup. The same physics that governs the drift of galaxies governs the vibration of the atoms in your bones. The observable universe is a practical limit, like the horizon at sea. Sailors did not mistake that circle for the end of the world. They used it to navigate. We should do the same. The fact that we cannot see beyond a certain distance does not mean there is nothing there. It means the cosmos has a history, and we are inside it. Let's close this section by stitching together the main points in one breath. The observable universe is everything that has had time to send us light since the fog of the early universe lifted. Because space expands, the moving distance to that horizon today is about 46.5 billion light-years, making the whole observable diameter about 93 billion light-years. Distant galaxies are not racing through space faster than light. Space between us and them is stretching. The expansion is accelerating, likely because of dark energy, which creates an event horizon, a limit on what signals sent now can ever reach. We see the cosmic microwave background as the oldest light, the afterglow from when space turned transparent, and we use its tiny ripples as a ruler to measure geometry and growth. Space looks very flat on large scales, which hints that the total universe is far larger than our observable patch. It may be infinite, it may be finite but unbounded. Inflation likely made our local region vast and smooth. The exact totals of galaxies and stars are still being refined, but the broad picture is stable. A uniform, expanding cosmos, linked by gravity into a web, with islands of matter afloat in oceans of space. To deepen the picture, let's talk about the clock and the map that cosmology uses. The clock is called cosmic time. Imagine averaging over all the lumps and bumps to define a smooth background universe. Cosmic time is the time kept by observers who ride along with that smooth expansion, not rushing through space in any special way. The map is laid out in co-moving coordinates. Co-moving means you mark positions on the grid that expands with the universe. Galaxies that simply go with the flow keep the same co-moving coordinates even while their proper distances grow. The scale factor is a single number that tells you how big the universe is relative to some reference time. When the scale factor doubles, distances between co-moving points double. When the universe was half its present size, the scale factor was 1/2. Redshift ties directly to the scale factor. If light leaves a galaxy when the scale factor is small and arrives when the scale factor is larger, its wavelength is stretched by the same factor. That is why redshift is a measure of how much the universe has expanded during the journey of the light. Because our senses are terrible at huge numbers, it helps to build a simple mental ladder of time and distance. A few waypoints work wonders. The moon is a little more than 1 second of light time away. The sun is 8 minutes. The nearest large galaxy, Andromeda, is a couple of million years. The disk of the Milky Way is 100,000 years across. The most distant galaxies we have seen are billions of years in look-back time. The last scattering surface of the cosmic microwave background is almost the full age of the universe in look-back time. But the co-moving distance to the matter that emitted those photons is many tens of billions of light years because of expansion during the flight. There is another distance often mentioned in popular explanations, the Hubble radius or Hubble sphere. It is defined as the distance at which the simple Hubble law, with today's expansion rate, would imply a recession speed equal to the speed of light. It is a useful scale for intuition, but it is not a strict horizon. Light from beyond that radius can still reach us because the expansion rate changes over time, and because the photon's journey is not a single frozen stretch, but a path through a changing universe. Horizons in general relativity are global, not just local snapshots. We also need one more piece of vocabulary: surface brightness dimming. When you look at a distant galaxy, redshift not only dims the light by spreading the energy of each photon, it also stretches time, so fewer photons arrive per second, and it stretches the image, so the same light is spread over a larger apparent area. These effects pile up as the square of the redshift factor for surface brightness. This is why the faintest, earliest galaxies seem ghostly even to our best telescopes. The universe does not just push them far away, it turns down their contrast against the dark. Because all of this is abstract, let's drop an analogical anchor. Picture an old film projector. The film reels are the history of the universe. The projector bulb is the glow of the cosmic microwave background, washing everything with a soft, uniform light. The frame rate is the expansion rate. Some frames are of a hot, dense plasma. Later frames show galaxies condensing along tidal lines of gravity. We cannot rewind beyond the moment the fog cleared, because there is no optical footage before that. But we can infer earlier frames by the patterns etched into the later ones, the way you can infer a plot from the scars on a hero's face. One of the most haunting realities in cosmology is this: there are regions of the universe we can see now, but which we will never be able to reach, and there are regions we will never see at all. To understand why, Imagine drawing a cone that widens as time goes upward. The tip of the cone is you, here and now. The walls of the cone are made of light rays that could arrive at your location. Everything inside the cone is in causal contact with you. Light or gravity or particles could, in principle, influence you from within that region. That is your past light cone. Now imagine a different cone opening into the future. Everything inside that cone can be affected by something you do now. That is your future light cone. In an accelerating universe, the future cone has a ceiling. The event horizon is a boundary beyond which signals we send today will never be able to cross and still catch up with the expansion. Some galaxies are inside our past light cone, so we can see them, but outside our future light cone, so they can never hear back from us. There is no contradiction here. It is just geometry in a dynamic space-time. This geometric picture has a poetic consequence. The night sky is a museum of messages from regions that are already beyond the reach of any reply. The oldest messages carry a weather report from when the universe first cleared. The younger messages carry photographs of small, awkward galaxies undergoing their first growth spurts. The nearby messages show grand spirals and giant ellipticals, star factories and star graveyards, gas plumes and dust lanes. All of them together sketch a single story of emergence. Gravity gathering, radiation cooling, chemistry starting, complexity blossoming. At some point in the far future, the museum lights will dim. Not because the universe grows tired, but because the wavelengths of distant light stretch beyond the sensitivity of any local detector, and because fewer galaxies will remain within our event horizon. The sky will look more and more parochial. The cosmic background will cool further. The slow burn of red dwarf stars will dominate. The great story will still be true, but it will be far harder for new astronomers to reconstruct it. We live in a lucky epoch, late enough to see a rich, structured universe and its ancient afterglow, early enough that accelerated expansion has not erased the evidence. There are a handful of ideas that reliably tie our neurons in knots. Untangling them makes the size of the observable universe easier to accept. First, there is no center of the expansion in space. The Big Bang was not an explosion of matter into empty surroundings. It was the rapid expansion of space everywhere at once. Every galaxy that is not gravitationally bound to its neighbors sees all the other distant galaxies receding, roughly proportional to distance. If you stand in any one of those galaxies and draw a circle showing how far you can see, your circle looks the same size to you as ours does to us. Second, faster than light recession is not a speed through space. It is a rate of change of distance because space itself is stretching. Relativity's speed limit applies to objects moving locally through space, not to the growth of space between distant commoving points. No galaxy is buzzing past its local neighbors faster than light. Over large scales, the accumulation of many small stretches can sum to more than a light year per year in separation growth, and that is okay. Third, the observable universe is not the same as the whole universe. The observable patch is simply a sphere of causality centered on us for practical reasons. We are doing the observing here. Someone unimaginably far away would draw their own sphere, overlapping ours in some region, and would be equally justified in calling it the observable universe. The whole could be vastly larger or even infinite. Fourth, the cosmic microwave background is not the remnant light of exploded stars. It is the stretched out glow of the entire universe when it first became transparent. It bathes the sky uniformly down to tiny fluctuations of temperature and polarization that tell us about the seeds of structure. It is the oldest light, not the light from ancient suns. Fifth, there is no credible evidence of a sharp physical edge. An edge would pick out a special direction and would likely leave a detectable imprint on the sky. What we see instead is remarkable uniformity at large scales. Our limits are temporal. How far light has gotten in a universe with a history. The numbers behind the 93 billion light-year diameter are not plucked from a single equation on a whiteboard. They are stitched together from several methods that cross-check each other. There is the distance ladder. Parallax gives us direct geometric distances to nearby stars. Standard candles extend that reach outward. Cepheid variable stars and Type 1 supernovae have predictable brightness patterns we can calibrate. If you know how bright something is intrinsically, and you measure how bright it appears, you can infer distance. This ladder has rungs and handrails built by decades of careful observation and recalibration. There is the clustering of galaxies. The imprint of early universe sound waves left a preferred scale in how matter clumps. That scale, called the Barrian Acoustic Oscillation Scale, acts as a standard ruler at later times. Measure the angle that ruler spans on the sky at different redshifts, and you get the expansion history. There is the cosmic microwave background itself. Tiny variations in temperature and polarization across the sky are like a detailed fossil record of conditions when the universe was 1 baby-year-old in cosmic terms. Fitting a model to those variations yields precise combinations of parameters. How much matter there is, how much radiation, how much dark energy, how fast expansion was proceeding then, and the overall geometry. There are also gravitational lenses and standard sirens. Gravity bends light, so massive foreground galaxies and clusters magnify and distort the images of background galaxies. The pattern of bending tells you about the mass in between, including mass that does not shine. And when two massive compact objects spiral together and merge, they launch ripples in space-time, gravitational waves, that carry a built-in measure of distance. If you can also identify a light signal from the same event, you get distance and redshift in one go, which gives another rung for the ladder. No single method is perfect. Dust hides things. Calibration can drift. Assumptions can bias results. That is why it matters that these methods overlap. Where their answers agree, confidence grows. Where they tension each other, we learn where to look for new physics or for subtle errors. When the fog lifted at a few 100,000 years after the beginning, the universe was a uniform, warm bath with tiny ripples. Gravity amplified those ripples. Regions with slightly more matter pulled in even more, and over hundreds of millions of years, the first stars flickered on. These first stars were likely massive and short-lived, made of pristine hydrogen and helium forged in the first minutes after the beginning. They died quickly, exploding and seeding space with heavier elements. Those elements, carbon, oxygen, silicon, iron, are the building blocks of later stars, planets, and eventually life. As more stars formed, their ultraviolet light reionized the neutral hydrogen fog that still filled space between galaxies. Reionization was a long dawn rather than a sudden switch. During that dawn, galaxies were small and chaotic, and the intergalactic medium became a patchwork of ionized bubbles that grew and merged. When we look out with our most powerful telescopes, we see hints of this dawn in the way light is absorbed by intervening hydrogen at specific wavelengths. We also see it indirectly in the small-scale features of the cosmic microwave background's polarization. All of this matters for the size question because it anchors our model of the expansion history. We know how the mix of matter, radiation, and dark energy changes with time. we know how that mix affects the growth of the scale factor. When you integrate that history from the beginning to now, you get the co-moving distance to the farthest light that can arrive. That is the 46.5 billion light-year radius. Change the ingredients or the recipe, and the number moves. Keep the ingredients consistent with the sky we see, and the number settles into a narrow band. Because the numbers are unwieldy, a small atlas of analogies earns its keep. Think of the observable universe as the part of a city you can explore on foot before sunset. The city continues beyond the ring of streets you can reach in time. Your map at night is not the whole city. It is the part your day allowed. The next day you could reach farther, unless the streets themselves stretch, moving the neighborhoods away faster than you can walk. In our universe, the streets do stretch, and the far neighborhoods are drifting beyond reach even as we mark their positions on last night's map. Or imagine ripples on a pond. Throw a pebble at noon, the rings spread outward. By evening, the farthest ring has reached a certain radius. That ring is like your observable limit for any signal you launched at noon. If the water itself were somehow stretching as the ripples moved, the radius you would measure at night would be larger than the simple speed times time estimate. The stretching changes what distance means between two ripples. Or picture the night sky as a layered cake. The nearest layer is our Milky Way, bright frosting and sprinkles. The next layer is the local cluster and supercluster, thicker cake, airy pockets. Then come the long filaments, thin, sugary threads. The farthest layer is the smooth, cool sponge of the cosmic microwave background. You can slice deeper by building a better knife, bigger telescopes, better detectors, but the bottom layer remains the same recipe. You are not hitting a plate. You are hitting a change in ingredients. The size of the observable universe today is one number. The fate of that size is another story. In a universe where dark energy behaves like a cosmological constant, accelerated expansion continues. The particle horizon keeps growing, but it grows more and more slowly in terms of new co-moving volumes that come into view. The event horizon remains as a limit. The space between unbound structures grows exponentially. Star formation declines as gas is used up or blown out or locked up in long-lived small stars. Stellar populations age. Planetary systems freeze and darken. Black holes slowly evaporate over time so long they are more chant than clock. There are other speculative endings in the literature, each with different conditions. A big rip would occur if the acceleration itself grew stronger over time in a particular way, tearing apart bound structures. A big crunch would occur if the expansion reversed, which would require a very different mix of energies than we infer today. A big bounce would require new physics that replaces the singular beginning with a cyclic or rebounding scenario. These are interesting to explore, but none of them change the present tense fact. Our observable universe is a horizon set by a finite age, stretched wide by an expanding geometry. After so many cosmic miles, it helps to remind ourselves what this means for us. The size of the observable universe is not a number designed to make you feel small. It is a number that says, here is how far reality has had time to speak to us with light. It is a measure of history, not of worth. It says our instruments and our patience can pull whispers from almost 14 billion years ago and weave them into a story we can carry in our heads. This story is practical. Satellite engineers use relativity to synchronize clocks, because time runs differently in orbit than on Earth's surface. Radio astronomers use the slight delay between antennas to synthesize giant eyes on the sky and image black hole shadows. particle physicists recreate early universe conditions in accelerators and read off properties that feed back into cosmology. Climate scientists use the same radiative transfer physics to understand Earth's atmosphere that astronomers use to model starlight through interstellar gas. The tapestry hangs together. The same equations flow from the very large to the very small. You can drink from that unity without drowning in the scale. Say it simply. The observable universe is everything that has had time to send us light since the early fog cleared. Because space expands, the co-moving radius of that visible bubble today is about 46.5 billion light years. That is why the diameter is roughly 93 billion light years, even though the age in years is only about 13.8 billion. Distant galaxies are not sprinting through space faster than light. The distances between co-moving points are stretching. The expansion is accelerating, which creates an event horizon limiting what could ever receive a signal from us if we sent one now. The oldest light we can see is the cosmic microwave background, the cooled down glow from when the universe became transparent. Its tiny ripples tell us the geometry is very close to flat, which suggests the total universe is far larger than our observable patch and may even be infinite. We measure all this not with a single trick, but with many cross-checked methods. Parallax, standard candles, standard rulers, gravitational lenses, and more. Beyond our horizon, the universe continues. It is not an edge. It is a limit set by time. So how big is the observable universe really? Big enough that our words creak. Big enough that even careful metaphors wobble. Big enough that our entire galaxy is a dot in a thread in a web inside a sphere that is itself only the part we can see. And yet, it is graspable. It has a number. It has a method. It sits inside a story we can tell, end to end, with the light on our faces coming from a sky that is both map and memory. If you walk down to the beach at night and look at the line where the ocean meets the sky, you are not seeing the world end. You are seeing how far you can see tonight. The universe is like that, beautiful, finite to our eyes, open beyond our sight. The horizon is not a border, it is an invitation. Tomorrow, with better instruments and sharper ideas, we will read a little farther. The city will not end where our streetlights fade. The dark will not be empty. It will be simply unvisited. And the part we can visit, the part we can chart with light and patience, already contains enough wonder to last many lifetimes. When you close your eyes now and picture that 93 billion light-year wide bubble, do not imagine a glass sphere around all that exists. Imagine a living history, a shell of messages arriving from every direction, written in many inks. Starlight, microwaves, neutrinos, gravity waves. Each message is a postcard from some earlier chapter. Stack the postcards in date order and you have a tale of cooling, clumping, shining, and thinking. Somewhere near the end of the stack, a small blue world looks up, measures carefully, argues about calibrations, refines the models, and dares to say a number aloud. That number is not the end of the conversation. It is how the conversation begins. And that brings us to the end of tonight's story. I hope you found it calming. Maybe you learned something new, and maybe you're already drifting into sleep. If you enjoyed this, please like the video and subscribe to Sleepy School. It helps more people find these stories and join us each night. I'd also love to hear from you. So let me know in the comments where in the world you're listening from tonight. For now, rest well, dream deeply, and I'll see you tomorrow night with another bedtime lecture. Good night.